Wait for the red light. The red light's on. Excellent. All right. Well, welcome back to our last class. And unfortunately, we don't have time for a review. Or maybe I'm choosing not to do a review, and maybe I'm choosing to give you something that's more important than a review. And what that is a little bit more on noise. And my view is that there's several fundamental processes of noise, and we really should at least introduce you to a handful of these. And so tonight, what I'd like to do is I have lectures on this. This is shot noise, which is a very insidious and very interesting kind of noise. And I like to lecture about this because I can wrap it up into one lecture. Whereas the other noise that's very pervasive is thermal noise, or Johnson noise, and that's also a very fundamental formula. Anything with temperature will give you a noise source, but that takes me 2 lectures to give. That's a 2 lecture based on the pieces that you know and how I can thread those together into a final answer. It takes me 2 lectures to do that. This one only takes me 1 lecture to do, and so I end up doing this lecture a lot more than I do my thermal noise lectures. It happens. So this is shot noise, and it's the fundamental noise that comes about because of a quantum process, a quantum mechanical process. And what I like about this lecture, and what you will maybe like about it, or also maybe not like about it, is the fact that it requires to get to the noise, we need a little bit of physics, although not very much at all, and we need an awful lot of review of stochastic processes from probability and statistics. And so what it'll do is the high-level thing to look out for is how you use some of the tools from probability and statistics in formulating the noise formulas. Okay? One of the things, for example, that we saw last week when we were doing the noise from the pulse code modulation, the MAP receiver, we saw the importance of the average and the mean. The average and the standard deviation. And so again tonight we'll see the importance of the mean and the average and the standard deviation in deriving a very, very fundamental formula for the shot noise. Now, shot noise is a very interesting formula because it's predicated on the fact that an incoming quantum or an incoming signal or an incoming photon, call it what it is, will arrive at the detector, and it has a well-known energy level. So it should trigger a well-known current level, which should trigger a well-known signal level. But we don't know exactly when that photon arrives at the detector. There's some uncertainty in the arrival time. There's some uncertainty in jitter, the jitter of the system. And what that translates to is a deviation in the time axis translates to a deviation in the voltage or the current, the vertical axis. And so you could see the interplay of that. Certainly with the eye diagram, you saw the interplay of that, and this brings it out in a different dynamic. And so when you think in terms of error bars, you should think in terms of error bars on the x-axis and the uncertainty in the y-axis as well, because both of those lead to an uncertainty in exactly where your point is located on the graph. Okay. I often say that what seems to happen is for an undergraduate curriculum in engineering is you learn to calculate the point on the graph, and then in graduate school you learn to calculate the fact that you have errors and uncertainties associated with that point. And I'm never going to stop trying getting the uncertainties into your head so you're more valuable as graduating. And that's part of the reasons for today. Okay, so a little bit of background on where this came from, and so this is sometimes called photon noise. It's shot noise, and it begins with something that's very archaic called a photomultiplier tube. And now, the common incarnation is an avalanche photodiode, APD, an avalanche photodiode. So you can think about an avalanche photodiode to some extent as a solid-state version of a photomultiplier tube. And but the old-fashioned glass-blown photomultiplier tube is a little easier to understand from a physics perspective. And so I'll walk you through that that qualitative understanding, and then the APD, a little bit more tricky, a little bit more subtle, falls out of that as well. And it begins with a metal detector, phosphor if you want, or rather just a low work. Well, okay. So the photoelectric effect. The photoelectric effect, which is really what Einstein won his Nobel Prize for. It wasn't relativity or anything like that. It was the photoelectric effect. And it was actually the birth of quantum. And because what he noticed was when he sent in light onto a metal surface, depending on the type of metal, what he would find was that sometimes an electron would pop off that surface. And so just if you think in terms of, say, gold has a yellowish color, right? It's a yellowish color. And so if you send in a red wavelength light, red or infrared light, nothing much would happen. If you sent in a blue or an ultraviolet light, however, you would be above the work energy, the work function of that metal, and the energy would have enough. The photon would have enough energy to liberate an electron from that surface. Okay? And so you had to conserve power, you had to conserve energy, and so the quantization of energy relative to this surface was the beginning of a postulate of quantum mechanics. Okay? And so then you have this electron liberated, and you can turn this into a detector, right? But you can't really do much with the electron, particularly if you're right at that work function, where this electron has been liberated, but it doesn't have any excess energy. That's not going anywhere, so it's just hanging out. This is all in a vacuum tube, so it's just hanging out in vacuum, just waiting to do something. And if you put another electrode next to it, and you charge it up to some voltage, then this electron will see a force from that voltage. The voltage differential there is the same thing as an electric field, and the electric field will give you a force. And if you're careful about your minus signs, then the electron will accelerate, F equals ma, QE equals ma, towards that electrode, and it may have started with no kinetic energy, 1/2 mv squared, but by the time it hits that electrode, it's chugging along pretty much, depending on how much voltage you've charged it to, depending on how much volts per meter are in your electric field. And so if that electron is now sufficiently above the work function, then two electrons might come out of there, and they might just barely make it off that electrode, but they're now liberated. And I can repeat the process with another voltage, and I can multiply the single photon that comes in if I keep doing this. So 1 becomes 2, 2 becomes 4, 4 becomes 8, and so on and so forth, until I actually have built up a pretty decent signal. Okay? So photomultiplier tubes are still sort of floating around, especially if you want to do stuff in the blue UV region. But for the most part, avalanche photodiodes and gallium arsenide have taken over the reddish IR range, and you can make them out of indium phosphide for the telecom wavelengths. So this does have application, for example, as a receiver. As a receiver, the APD made out of indium phosphide is a popular choice for a detector or receiver detector in a fiber optic system. Okay. All right. Well, that's sort of the physics behind it. And what we should do is we should kind of think at these photons here are going to arrive. They're going to arrive with some uncertainty in the time. And so the final current, or the final electrons, they're emitted with random delays, and that random delays has caused a noise, is what we will call a noise. So we'll say R is the rate of photon emission events, and a rate is 1 over seconds. Okay, so this will be the number per second. So the number of photo emission rates divided in a certain time. Okay, we're shifting more and more towards your probability and statistics course. So we have an uncertain arrival time. Does anyone remember what kind of statistics that is? Poisson statistics. Excellent. So this lecture will be, in fact, a review of some of the highlights of Poisson statistics. Okay. So this average rate of photon emission events, if this were a probability and statistics class, you'd be thinking the bus comes. There's one bus every 15 minutes. I show up at the bus station. What is the most likely, or the bus stop? What is the most likely time that I will have to wait for that bus? Okay. So depending, you might have just missed it, in which case you have to wait 14 minutes and 30 seconds, but you don't know that. And so these processes are governed by Poisson statistics, and that's what we will discover here as well. Okay, or rediscover. In this case, though, we can relate this R not to a bus schedule, but rather some of the properties of our detector. And so there'll be an efficiency for the detector. I generally like to use ETAs for efficiencies. I think a lot of people do as well. You were making fun of my Greek letters a couple of lectures ago, so I now have to explain myself for all of these. I kid. There's a power. Clearly, the brighter the beam, the more events I'm going to have. And power is measured in watts. And another way to write watts is joules per second. So if I'm looking for numbers per second, I just got my per seconds out of the whole units. And remember, this is a quantum effect. This is fundamentally a quantum effect. A single bus, a single photon coming in. And so what we can do is we can divide through by a magic quantity h nu. So h is Planck's constant, which you've probably seen before in like a devices course. And nu is the frequency, as in lambda nu is equal to the speed of light of the photon. So most of the world will specify a color as a wavelength. 500 is about green, 600 is about red. But we don't, engineers are suspicious of wavelengths, and so we like to specify them in terms of frequency. We know from our electromagnetics class that that the wavelength changes with materials, and it's the fit to the solution to the differential equations. So things like the structure of things in authority, like the structure of an atom or a molecule, or the FCC, they are the ones that give rise to the frequencies, and the wavelengths follow around. Okay. H is Planck's constant. It's the fundamental heart and soul of quantum mechanics. This energy is equal to h nu is a fundamental formula that says light is also a particle as well as a wave. My rule of thumb is when I see H in a formula, I know that quantum mechanics has been there. And when I see K in a formula, I know that classical statistical mechanics, Boltzmann's constant, has been there. So H turns a frequency into an energy. K turns a temperature into an energy. KT is an energy. And if you think back to devices, you'll remember perhaps that there are formulas that compare h nu to KT. E to the minus h nu over KT, for example, comes out a lot. Okay? And there you're comparing the amount of the quantum effect to the amount of the classical effect. Okay? Just again, a little bit of a reminder in there. Okay? And so what this is saying here, if I put these guys together, it says that power is equal to h nu times the number of the photons per time. Okay? Now, n bar is the average number of photons that occur in a particular time t. Or I guess I should call them photo events, because I have this detector efficiency there. So if a bus comes on average every 15 minutes, then on average I'll get four buses in an hour. There's a chance I'll get 3, and there's a chance I'll get 4, and there's a chance I'll get 5. But that's just the nature of the statistics of the bus company. So we don't really care though about any given particular capital T. That comes in later on in our system. So what we'll do is we'll divide T into n segments. Okay? So I'll divide it into n segments. And in any one of these segments, the average number of events occurring in any one segment is capital N bar over N. And that's sort of a piercing glimpse into the obvious. Right? If I've got 4 buses coming in here, and I divide them back down, I divide them into 30-minute increments, into two sections, I'll have 4 over 2, which is 2. Yeah? But the idea here is to let n get very large so that n bar over n is much less than 1. Okay, so instead of dividing the hour into 2 segments, we really should divide the hour into 60 segments. And if that's the case, then this is the probability that one event occurs in a particular segment. Okay. And again, the nice thing about this proof is if this isn't true, then I just increase n, little n, until it is true. Okay. N bar over n, capital N bar over n, is the probability that one event occurs in a particular segment. If I consider capital N specific segments, okay, in this case I've circled 3, but if I consider capital N specific segments, then the probability of being here, here, and here, of getting a photon here, here, and here, or a bus here, here, and here, is this probability multiplied by this probability, multiplied by this probability. So it's just that probability raised to the nth power. So this is the probability. Probability that events occur in n specific segments. And the probability that no event occurs in that segment is 1 minus n bar over n. Okay? So if this is the probability that an event occurs in this segment, then 1 minus that is the probability that it doesn't occur in that segment. And I have capital N, I have little n segments. I have little n segments, and I've chosen capital N winners. So, little n minus capital N is the probability that an event does not occur in n minus n segments. Okay. Okay? Now, do they add up to 1? Well, you could probably figure that out faster than I can. But where we're really going to is the probability that exactly n events occur in capital time T means that I have n bar events over n occurring in capital N segments, and so that's a multiplication. I have 0 events occurring in n minus n segments. Okay? And I now have to count up the number of choices or the number of permutations that I have for these n segments out of little n segments. And so that is n choose n. There's the formula. I think of it as n choose n. I know. That's why I think that's why I like giving this lecture, because you've seen that before, and this rattles it out of your dusty cobweb of a memory a little bit. Okay, and trust me, I have to go back and pull my stat books out to remember these things. Maybe you won't, because maybe you'll work with this so much. That would be fun. But this is the total number of ways that n events can occur in n segments. And does anyone recognize what this is called? Oh, let me make sure I label this. It's a probability. So that's P, and it's discretized into a certain number of slots, and it is a function of capital N, the number of segments. Okay. Does anyone remember what that distribution is called? Very, very, very good. Awesome. See, a professor that doesn't like to talk as much as I do would have just said, "Oh, obviously we have a binomial distribution that you've learned about in probability and statistics, and there it is." So at least I took a little bit of time to refresh what each of those three terms are in that binomial distribution. Okay? Now we're going to rearrange terms a little bit. This is capital N bar to the n, and this is little n bar to the n. And what I'm going to do is I'm going to slide this guy over here underneath there. And so when I do that, When I do that, I can write n factorial, n minus capital N factorial times little n to the n factorial. I can write that as a sequence.
So you have capital N events on the top, and okay. And then
N bar is the average rate. Little n is the number of segments. This is a discretized view. We'll change that in a little bit here. And then we have n different events. So how many buses come in an hour? 4 buses come in an hour. And how many would come in any minute of an hour? And for any 4 specific minutes in an hour. Okay? So that's what this front term is doing to us. I have this constant, n bar to the n, there. And then I have this last term here that looks like that. Okay. So just a small rearrangement. But now what we can do is we can start to remember or recognize some of the formulas that we learned about maybe as a curiosity in high school. If we let n go to infinity, then I get the probability of n at any instant of time which gets me this. Now, what's nice about this formula is you see that n occurs in the denominators, and so there's a nice taming or linearizing of all that to balance with this n going into the in the exponent. Yeah. Wait, tell me when to stop. There?
Yeah.
So what I did was this guy here is n bar to the n divided by little n bar to the n. And so this guy here is sitting here. This guy here goes into here and cleans up my formula. So this formula here is actually n bar over n bar, n minus n multiplied by n to the n. Okay? I should have made that explicit. I said it in words, but that's never enough when you're doing math. Okay? All right. So when this happens, I'll clear out all the stuff that's independent of capital N. That's this term here. All that stuff goes away. All these terms vanish. And so this is just 1. It's a really dirty trick. Really fortuitous. And I'm left with this 1 minus capital N bar over N. So I have a big number in that denominator. But to balance it, I have n minus capital N, so I have a big exponent. So I have a big exponent there. So this is n bar to the nth over n factorial. And this limit here is my exponent. I think that's usually taught in like a calculus class in conjunction with compound interest. I think that's usually taught in that context because finance is supposed to wake everybody up because it has to do with money. But a nicer way to do that is just to plot this for n equals 100, 1,000, 10,000, and so on, and you can see how it'll get to that exponent. Okay, this distribution here is the Poisson distribution. And we're now going to look at some facts of this. If I add up all the possibilities of capital N, this is the probability of this formula here is the probability of having a particular capital N occur in that length of time. I could have 0 buses show up, I could have 1 bus show up, I could have 2 buses show up, 3, 4, 5, 6, 7, 8. In principle, I could have an infinite number of buses showing up in that hour. So I want to add up all those possible probabilities. This guy, here's my negative e to the minus n bar, and this guy, when I sum all this up, gives me e to the positive n bar. Multiply those together, I get 1. Therefore, the probability distribution is normalized. Okay, the area under that curve is 1. So all the possible outcomes, the probability equals to 1. That's usually a good thing for probability distribution. Now, we want a type of average to find out what the most likely event is going to be, or the most likely n. And so we're interested in the expected value of n. And this is going to equal the first moment of that distribution. Okay? That's going to equal the first moment of that distribution. The weighted average, if you want to look at it that way. Okay. So that's equal to oops. Notice the dirty trick I did with my indexing. If n is equal to 0 here, then there's no term, so I might as well start it at 1. Right? This is equal, so n equals 0 to infinity is the same as n equals 1 to infinity. So notice when I multiply through by this guy here, I have an n factorial in my denominator. That's n times n minus 1 times n minus 2 times n minus 3. But I have an n in the numerator. So that's those two. The first term cancels. So that's just n minus 1 to infinity. I can also factor out one of my n bars here, if I want to. Okay. Now I'm going to make a dummy variable change. Here's my counting number, here's my counting number. This is an n bar and this is an n bar. So this is going to equal n bar times the sum, and I'm going to say m equals 0 to infinity of n bar to the m over m factorial e to the minus n bar. And that's just equal to n bar, as we found out before. This guy is going to be normalized to 1, and we're going to be left with just n bar. So the expected value is the average value. And that's comforting. Very, very comforting. Okay. I'm guessing you've seen this before and probably forgotten it. So I'm just going through. And really my point to doing this is to refresh your memory of the probability and what it means to be normalized. And then the expected value, that's the most likely number of buses per hour. That's the most likely number of events that we see. And then how do you calculate that? Well, this moment analysis, right? This weighted average, this moment analysis. Okay? And so if you remember back to our eye diagram and our histogram for the MIP detector, the most likely voltage for a 1, the most likely voltage for a 0. M1, M0. This is how you would calculate that if you didn't want to assume a Gaussian distribution. Okay? I find these weighted averages, this moment stuff, very, very, very useful to think about. Okay? It comes up all the time. We want the standard deviation because we're doing a noise problem. The uncertainty or the variable, the variation in this distribution, and that's the next higher order moment. So if the summation of all the possible ends was just the normalization, the first moment gives me the expected value, the most likely value. Then the variation on that is going to be related to the second moment. Now there's a nerdy little trick here. Notice that n squared can be written as n minus n plus n squared. So if that's the case, then I can rewrite this guy here like that. Okay? And the nice thing about this is here's my first moment, and I just went through 3 or 4 whole lines of algebra to show that was n bar. And I'm going to add to that that guy there. And I'm supposed to start at n equals 0 here, but if I plug a 0 or a 1 in there, I get 0. So I might as well start there. And I'll be now explicit. About what my probability distribution is. So now I'll factor out an n bar here. So I'll factor out an n squared here. What I'm left with, this guy is n times n minus 1 times n minus 2 and so on. So I'll divide those guys up there and get the n minus 2. And then I have an e to the minus n bar. Almost done. I play exactly the same trick I played before. This is equal to n bar plus n bar squared. Here's an n minus 2, an n minus 2, and an n equals 2. Change my dummy variable. This guy then is, we've seen was normalized to 1. So the expected value of n squared is equal to n bar minus n bar squared. The variance? Sorry, what?
Where's the net minus come from?
Oh, a mistake. Sorry. Good call. Thank you. I would have been floundering here in a second. So the variance is e of n squared minus e of n quantity squared. That's sort of just the definition. This is equal to n bar plus n bar squared minus, and here's the expected value of n is n bar, but I need it squared. So the variance is the same as the standard. The variance is the same as the expected value for this distribution. And finally, what we care about is the standard deviation, and that's going to be equal to the square root of the variance. Okay? So again, that's just a guided tour through the moments, through the variance, through the expected values, and so on. All right, back to our problem at hand. The current, the average current, is going to be the charge on the electron times the number of events in a given time tau. And this tau is probably going to be some averaging time. Probably going to be some sort of RC time constant over which I'm integrating. So the noise of the photocurrent is going to be the variance of I of t. And we went through all that. Our units, e squared over tau squared, times the variance of n, and that's going to equal e squared over tau squared times n bar which is equal to e squared over tau times I bar, the average current. So rearrange this for n bar, shove it in there, we get to cancel, 1e and 1 tau. If this RC is equal to 1 over delta F, the bandwidth of my filter, then the noise times delta F. And this is called Shakti's formula. So this is called either shot noise or Shakti's noise for two different reasons.
For the noise of the event for I sub n squared equals, what is the symbol on something, the term with the hat on it, on the middle of the page? Yes.
The variation in the current.
Okay.
The variation in the current. Okay, now, if that's the noise, we can look at the signal power divided by the noise power in this system. And we know that the I signal was the efficiency of the detector, the charge of the electron, times the average power of the signal, divided by the h nu. So PS over h nu was the number of events. There's a conversion efficiency from photons to electrons. And to get me from a rate to a current, numbers per second to electrons per second, I multiply through by E. This is I signal. I noise is equal to the square root of IN squared, which is equal to the square root of twice E IS times delta F.
What's E again?
The charge of the electron, because we're talking about currents now that are flowing. And we can substitute in for IS. Clean this up a little bit. And so now I have my signal and I have my noise. And so if I take the ratio, I get that. The E squared here will cancel with that E there. I can pull the 8 and the PS into there. And there's my signal to noise, my signal current to my noise current.
Is this in our book?
I don't know.
Okay.
But it's in your notes, and it's on Course Echo.
Okay.
And it's a very useful formula. Of course. I was going to do that anyway, but I wanted to... That's all right. No, it's okay. No worries. Everybody has it? Okay, good. The signal to noise formula, I'll just repeat it here, is eta PS over twice H nu delta F. So PS is the power of the signal that comes in. And this whole signal to noise ratio is current over current, a signal current divided by noise current. And so this is dimensionless. This has to be dimensionless. So eta over 2 H nu delta F, or rather 2 H nu delta F over eta, has to have units of power, and it's the power caused by the noise in a particular bandwidth. And so we call that P sub n, and this is called the noise equivalent power, so that the SNR is equal to 1. Has anyone run across an NEP spec in any of their work, any of their senior design work or anything else? Well, you may. You'll run across an NEP or noise equivalent power, and that's exactly what this means. It's the power of the noise such that the SNR is equal to 1. Okay. So these formulas for the noise and for the signal to the noise it represents how you would handle one fundamental kind of noise source in your system. So whenever I make a measurement, I can expect some uncertainty in the arrival time of the signal. That uncertainty leads to Poisson statistics. That those Poisson statistics, looking at the average, looking at the variation on the average, will give you a signal to noise. In this case, it's fundamentally related to the quantum nature of the particles that are carrying the energy into your system. Okay? So this is a quantum noise source, and it's one kind of noise. It is the lowest level of noise. It's the lowest dB level. Okay, it's probably the one that's least that's smallest in magnitude. Okay, so you have all the technical noises, 60 hertz, pollutions, impairments, and so on. You'll have A to D noise. The levels of how many bits you're keeping. That's your design choice. Then you'll probably have that thermal noise that I'm talking about. If you get rid of all of the other ones, the most fundamental, the lowest one, the one you can never get rid of, is this shot noise. So if you do shot noise, if you get to the shot noise limit, you're probably doing the very best you can. That's another reason why this is such a fundamental formula for you guys. This is the best you can hope your system will do. Okay? And there's a lot of tricky, wonderful designs that get you around this, that will get you to this limit. Using two differential detectors, for example. Very, very precisely arranged, very, very carefully arranged. The differential input will get you so very close to this, canceling out all the other noises. Okay? Like the input end of the input to an op amp is a differential input. You can imagine those transistors being detectors. Okay? Beautifully matched. So there's good news here, right? You can get there. The bad news is, because of the very nature of the quantum arrival statistics, you're gonna see noise. What I like about presenting this is you ask where noise comes from, and this is an example of a noise that just is natural, just in the natural physics of the system. The other reason I like presenting this is because so the formula here is very, very useful, and look at it, it's still very fundamental. It's the bandwidth of your system. We've talked about how important that bandpass filter is at the beginning of our receiver. The wider it is, the more noise you have, the lower your signal to noise ratio is. Okay, so directly right from the fundamental physics. The rest of it is h nu, the fundamental constant of conversion of a frequency to a quantum energy. Factors of 2, well, they're important, but they're there. And then eta is just the device inefficiency. So the worse you are with eta, the worse you are at converting your signal, the worse your signal to noise is. Okay? Okay. Let's see. I have one little permutation on this. Supposing you have, and this happens in a lot of situations, supposing you have more light that's incident or more signal that's incident on your detector than you do signal. In other words, supposing, let's see, we have room lights on in this room. Okay? I have exit signs that show that point the way out. Okay? If I'm looking at the photons from the exit sign, I'm also seeing all the light from my room lights. Okay? If I turn off all the room lights, then the exit sign lights are more vivid, right? the signal to noise of the exit sign lights are higher. So with all the other room lights on, there's a background, there's a clutter that further degrades my signal to noise. In other words, the arrival statistics of the photons from the cluttering are creating a noise equivalent power, the same way that the arrival statistics from the noise of the exit signs are also doing that. So to change this up a little bit, I'm going to define a new noise current, and I'm going to go back to this formula here. And my new noise current is going to be exactly what I had before, 2 eta E squared. I guess I'm stealing it from this version here. H nu in the denominator. Now, in addition to the PS, the power from the signal, I'm also going to have a power from the background. And then I have to remember how open my bandpass filter is. Okay? So all I've done is I've added, to add this background clutter, power from the background, I just adjust that signal power. Since this signal power, this is the source that's creating your noise, isn't that beautiful? For shot noise, the more power you have in your signal, the more noise current you have. Right? The arrival statistics itself give you noise. So the more of those statistics you have, the more uncertainty you have, therefore the more noise you have. That's why this is such an insidious noise source. The higher your signal is, the more your noise is. Now you've got the square root there, so you're winning, but you're not winning as fast as you want to. Okay? So if this is generating noise, then an additional background clutter is also going to contribute to that noise. So this is my signal, and this is additional noise due to a background. So my new signal to noise ratio is my old signal divided by my new noise current. I'll go through exactly the same math that I did before. So there's my signal, and here's 1 over my noise, H nu. And then I have 2 eta E squared. And then I have, instead of just PS, I now have PS plus PB times delta F. And this simplifies out a little bit to eta PS squared over 2 H nu PS plus PB times delta F.
So the little b is the same as the big B, right?
Oh yeah. I'll make them both big B's.
Can you scoot it up just a little bit?
Of course. That better?
Yes.
Now I can calculate my new noise equivalent power.
Can you bring it back?
Of course. I'm sorry. Yeah, absolutely. Yeah, it's messy. But everything's in there for a reason. The efficiency, the power of the signal, H nu, delta F. So the noise equivalent power occurs when my signal to noise ratio is equal to 1, which means when this guy here is equal to this guy here. So 1 is equal to eta PS squared over twice H nu times PS plus PB delta F. Multiply all this out. Here we go. 2H nu delta F PS minus the last term. So multiply all this out and I have the quadratic formula. So we're going to look for the PS's such that this is equal to 1. The signal drops down exactly when it's equal to the noise equivalent power, so that this SNR is equal to 1. So P sub n negative of B plus or minus the square root of B squared minus 4ACL over 2A. So Pn after simplification is equal to that. Sorry. Now, the math gives me the plus or minus, right? So I got to figure out which one I need. So this is going to be 1 plus something, or 1 minus something. And if I look at this guy here, this is always going to be greater than 1. Frequency is going to be greater than 1. Delta F is going to be greater than 1. Eta is going to be greater than 1. PB is going to be greater than 1. So this is going to be 1 plus something greater than 1. So this whole thing is greater than 1. The square root of that is going to be greater than 1. So if I have 1 plus epsilon versus 1 minus 1 plus epsilon, I can't have a negative number. Power must be greater than 0. So I can choose my root that way. And that's about almost as good as I can get it. The only thing I might add is if PB is very, very large, then I can calculate my PS. I'm sorry, I can get a slightly simpler formula for P sub n. Okay?
I guess it's just due to approximations? Or?
Yeah, that's just the approximation. So all I'm doing is I'm saying this guy's big relative to 1. And then I just multiply through, and I get that. Okay?